All right, welcome back. This is CSCE 156 and 156H, Computer Science 2. And last time we were talking about array-based lists, and we did a couple of demonstrations on building them, how they work, the advantages and disadvantages of each, and then we started looking at an alternative, a linked list. So let's review what we were looking at before. Each element in a linked list, each element is stored in a node. Each node stores a reference to the next node in the list, so it kind of looks something like this visually, and I just found this on the web. It's a nice data structure visualization tools. These are a dime a dozen out there. And so there's the head of the list here at the beginning. The end of the list is called the tail, and each node is connected or linked together to each other. So you start at the head, and if you want to go to the next node, then you traverse to the next node, next node, next node, next node, next node. So what we're going to be doing today is we're going to demonstrate how to build something like this. I'm going to show you a quick demonstration. I've already built a node class, and I'm going to explain that a little bit. But then we're going to go through some basic operations here. We're going to insert an element at the head of the list, maybe make some convenience methods, remove an element from the head of the list, and then we'll try to generalize this by inserting, maybe removing an element at the end, and then like we did last time, an index-based retrieval method or an index-based insert method. Okay, so to get things started, let's go ahead and take a look at my node class here, which I've already written. It has two elements. It has an item, and it's parameterized here automatically. That's something that we did last time for our array-based list. So that this node can hold any type. It could hold integers, it could hold doubles, it could hold strings, it could hold user-defined types like students or bank accounts or something like that. I've got one constructor here that simply creates a new node with the item that is given, and by default, it's not going to point to anything. So if I create this node, it's just going to point into the ether here. It's going to point to null. In fact, that's how we're going to tell whether or not it's linked to something else. We've got standard getters and setters here, but one thing I added is a Boolean method that returns true if it has a next node. And we do that simply by checking whether or not this node's next is not null. And if it's not null, then it has a valid node that you can traverse to. That's going to be really convenient over in our list implementation. Okay? So let's take a look at my linked list here. Again, it's also parameterized because I want to make a linked list for integers or for doubles or whatever you want. We're going to keep it simple and we're going to stick to integers for now. But what should the state of my linked list look like? Well, we're not going to hold all of these nodes in memory here. If we were going to hold all, let's see, 7 of these nodes, then we're back at square one with an array-based list. If you're holding on to references to all those things, then you might as well just have an array and have contiguous memory. The advantage of using a linked list is that these can be located in various different parts of memory, right? And then you can jump to that memory location just by simply going next, okay? So we can't hold everything as part of the state, but all we're going to be doing is holding the head as part of the state. So private node, same parameterization here, and I'll call it head. Right? Now I'm going to have to create I'm going to go ahead and create a default constructor for this. And it simply creates an empty list. Now, an empty list is simply when the head is null, right? There's nothing in there. It's not the head is invalid. There's nothing to reference because we haven't put anything into it yet. Okay, so there's the start of my linked list here, and this should run without issue because at least we haven't overridden the toString method here, but everything is initialized and set up for us to do something with it. So now let's go ahead and do this first method here of inserting at the head of the list. So public void insert at head, right? And of course we'll need to take an item. I'm going to parameterize that item. That item is going to be inserted at the beginning of the list. Now again, this visualization tool over here allows me to look and see what that visually looks like. I will insert the element 42 at the head of the list. And visually what that means is you're going to create a new node, you're going to make it point to the old head of the list, and then you're going to update the list's head reference to point to that 42. Okay? So let's go ahead and do that. I first need to create a new node. So new head. I'll call it the new head because I'm inserting at the head. And I'm going to make it hold that item that we were given as part of the input here. Now I need to do the second thing of making this new head point to the old head. So new head dot set, and I've got setters here. Set the next node to this head. Right? Now that ends up doing the second step where I've got the new head down here, and it's pointing to the old head. But what I need to do is now I need to make that the new head. So this dot head is equal to the new head, and we're good to go here. Now, if I did this in any other order, for example, what if I set this head is equal to the new head before I set the next head? Well, that means that I would lose reference to the original head of the list, and I would just be making the node point to itself, and that would really screw things up. So the order on this stuff is really important. You have to create it, then you have to set the reference, and then you have to set the head. Now to test this, I'm going to go ahead and insert elements 10, or actually, sorry, 100, 90, 80, 70. If I'm always inserting at the head, though, the state of this list after I'm getting all this done, after inserting 100, 90, 80, 70, all the way down to 10, is going to be in ascending order. Now, if I run this, obviously, it's not going to tell me what's in there. But if I go ahead and set a breakpoint here, and I run it in the debugger, then we can kind of see, let's look at the variables here. We can see this list, and here's the head, and it's got an item. That item is 10, and then it's got a next, and that item is 20, and it's got another next, and that item is 30, and it's got another next, and that item is 40, et cetera, et cetera. So you can see if I keep expanding this out, of course, I'm going to go 10 levels deep here because there are 10 things in there. That's not that convenient, though. So what, as a second exercise here, let's make it a little bit more convenient by overriding that toString method so that I can actually look at this thing. All right. So public string toString. Now I need to return a string representation of this, so I can't just print things out to the standard output. So I'm going to create a string builder. And ultimately return it. Now what I'm going to do is I'm going to traverse my list. So here, suppose that this is my list. I'm going to start at the head, and I'm going to say, okay, well that's 42. I will append that to my string builder. Then I need to go to the next. And I will will get the item out of that node, print the append it to my string builder, go on to the next, repeat that over and over again until I get to the end of the list here. So I'm going to go ahead and write this as a while loop because up front, at least in the current implementation, I don't know how big my list is. That's something that we're going to solve next. Okay. So while some condition, I'm going to have to set up a current node. So let me go ahead and create a node. This cur short for current. And where do I start? Well, I start at this head. Right. Now I'm going to update that, and current is going to end up being the head, then the next, next, until it gets to the tail end here, at which point it's going to be null. So while the current is not equal to null, and you'll notice immediately that this takes care of some corner cases as well, because if the list is empty, right, then the head is null. And so if I set up my current to be the head and it's null, then I immediately break out of this loop and we're done, right? And there's nothing to print. We might want to treat that as a special corner case, actually. Let's see what that looks like, though. So while the current is not null, then I want to append the value stored in that current node into my string builder. Current.getItem, right? And we'll just rely on the toString method of that item to get a string representation of it. Let me go ahead and also append a comma here, right, so that we have a nice comma delimited list at the end. Okay. And now I need to set myself up for the next iteration of this while loop. Current is going to be updated to current's next node. Right? So if current is currently pointing to this node and this is the next node over here, I need to update that, update that, update that. If my cursor is the current reference, then it initially points to the head, then the next, then the next, next, until it falls off the end of the list here. Okay. Let's see what that looks like now. I'm going to go back into my Java perspective. There. 10, 20, 30, 40, all the way down up to 100. Now we do have this trailing comma here. That's no big deal. Of course, you can stop short on your while loop here, and you can also take care of corner cases. For example, what if the head is immediately null? So we can take care of that by just treating it like an edge case or a corner case that we immediately return from. So if this list's head is null, then I'll return a string representation that's empty. I'll just return the word empty put in square brackets here. All right. Oops. Equals. There we go. So to test that, let me go ahead and look and see what the toString method does before I actually insert anything. And we see that it's empty, and then of course I insert 100, 90, 87, dot, 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 all the way down. I'll leave it as an exercise for how to get rid of that trailing comma. Here's a hint. You just need to make sure that this while loop stops short. That while the current node's next is not null, then continue, and then handle that last iteration outside the loop. But for now, this is pretty good so that we can continue to test and continue to work on things. At this point, I want to go back to insert at head and realize, well, if there's a corner case for toString, is there a corner case for insert at head? Well, is there? What if it's empty? What if this list head is null? Well, we still create a new head with the item. The new head is, we set the next to this head. If this is null, then that's okay. We're just setting it to null. It was null to begin with in the constructor of the new head, in this constructor over here. And so this is fine too. And then this dot head is equal to the new head. It doesn't matter if the old head was null or not. This has no effect on that. So we were taking care of all of the cases here with this very simple code in insert at head. All right, well, what else might we want? What about a convenient method here to determine the size? Okay. Well, we can kind of take code that we did with the toString method here. Let me go ahead and create another public method, public int, because of course sizes can't be half. So it's either 0, 1, 2, 3, etc. And I'll call it getSize. And it's kind of the same basic idea as the toString method, where instead of appending stuff, though, I will return 0, or I will keep a counter, right? In fact, I can create a counter here. I'll set that equal to 0, and then I'll return count if I know that, that the head is null and so that's an empty list. No need for a string builder anymore. I will go ahead and go into a while loop here, but instead of appending, I will say count plus plus. Right. I still do need to set myself up for the next iteration, and then at the end, I will return count. Okay, let's see if it works. I will print out the list's size. There we go. Run it, and there are 10 elements in there. If we did that before, then of course there's another corner case, and the size would have been 0. Right? And so that works. Okay. Now, you've got to think ahead here. Is this the best implementation of the getSize? Well, if we start out with an empty list, and we insert an element, and insert another element, and say that we've inserted 1 million elements, in order to compute the size, we would have to traverse over the entire list every single time if we to get the size. That sounds like something that we could probably keep track of. If we're inserting elements and we're taking away elements, maybe we can use like the same design that we had with the array list, where we kept the size as a variable and then updated that. Anytime that we inserted something, then we incremented it. Anytime that we removed something, then we decremented it. And so I'm going to make that optimization here now. Right? Of course, we need to make sure that it's initialized. An initially empty list is going to have size 0. And better practice, go ahead and use the this keyword even if it's not necessary. Okay. Now, every time I insert at the head, I will go ahead and make sure that the size is incremented. And now I don't need to do this while loop anymore. If I've got 1,000,000 elements in here, I'd be doing 1,000,000 traversals here just to figure out how many elements are in there. Instead, I can go ahead and get rid of this and return this list's size. And that's going to be way more efficient than recomputing it every single time, as long as you're keeping it stored somewhere. Right? And as long as we make sure that anytime that we need to that we remove something, we decrement that. Anytime that we insert something, we need to increment it. Okay. All right. So those are two very convenient methods that we'll use going forward here. Let's go ahead and now remove from the head. Right. So if we have insert at the head, then we might want to remove the element at the head. So I'll go ahead and remove from head. Right? And of course, we don't need to pass it the item, but we could return the item. Right? So if I'm going to remove the element at the head, then maybe I also want to return it. Of course, whoever calls this method could ultimately ignore it. In fact, we will when we test, or we'll just print it out, but we won't store it anywhere. Otherwise, if it was just a void function, then it'd be like deleting the head and forgetting all about it and throwing it away entirely. By returning it, though, we make this a little bit more versatile. You have the option of retrieving it and removing it from the head, and then you have the option of storing that into a variable and using that if you want, or just ignoring it. We're making this a little bit more functional, a little bit more versatile for people to use. All right, so we don't want to create a new node, right? But one thing that I do want to do is I want to take the element in the head and I want to save it off because I want to return it. So item is equal to this dot head dot get item. All right, and that's ultimately what we're going to return. All right. Now let's visualize this. I'm going to go back to my visualizer here. Let's remove the element at the head, the 42 that we just inserted. All right. Did you see what happened? All we did to delete this node was we made the head reference point to the heads next. And we're relying on Java's garbage collection to take care of cleaning up the node for us. So the way that we do that in our code over here is I'm going to want to make this list's head point to this list's head's next element. And that's all it takes. This head will now point to the next head. Let's see that again in the visualization. If I remove from the head, then 2 is going to end up being my new head. I'm just making this reference here now point to 2, and then this 22 basically disappears. Right? Easy enough. And of course, we need to make sure that we decrement the size. Okay. Now let's test this. I'm going to go ahead and go into another for loop here. There are 10 elements in here, so I'm going to let's remove them all. Oops. And now I've got that size, so I can go ahead and for each of them, I can go ahead and remove them. So list dot remove from head, and let's actually go ahead and capture that and print it out. So if I remove 10, 20, 30, 40, everything gets shoved down to become the new head. And if I do this, then I print it out at the end, I should get... Oops. I made a mistake here. I++. Oh, you know what? This is probably getting recomputed each time. So let me go ahead and put that into, there are a couple of issues here probably. And let's go ahead and do that. Oh, and then I'm printing 10, so X, that's what I wanted. Let's go ahead and run that again. And there, now it's empty, right? So my mistake here was recomputing the size, and it was decrementing and getting the new size every single iteration of that. Now I'm putting that outside the loop, capturing that 10 so that I know to remove them all. And then of course I was printing the wrong thing. I'm printing 10, now I'm printing that you remove 10, you remove 20, you remove all the way up to 100. What if I removed one more? Let's find out. And then let's print out the list. I got an exception. So let's go ahead and jump to that line, number 21, and let's think about this. So if the list is empty, then this head is going to end up being null. And if it's null, then of course I'm not going to be able to get the item because I can't call a method on a null element. So again, another corner case here. If this is empty, head is null, then let's go ahead and return null. That's one way that you could handle it. Or you asked for something that doesn't exist, or what if you were allowed to store nulls in this list? How do you differentiate between, okay, you stored null at the head, and then you returned it and you removed it. Well, here you go. Here's your null, versus when the list is actually empty. So another way that you could have done this is by throwing throw your own exception. So we could go ahead and throw new illegal state exception, right, of the you cannot remove from an empty list. Right? Now that's going to be a whole lot better than a null pointer exception, because now we're going to actually get a message that is relevant to what we're doing here. You cannot remove from an empty list. So throwing your own custom exceptions gives you a little bit more of a more relevant message to what's actually happening here. Okay. Or again, you could have returned null. Both of those are possible design decisions. But of course, then you would need to give them a way of differentiating and seeing whether or not this list is actually empty, which makes me think that maybe we want a method to do that. Is empty. Well, this is really convenient because we've got this size that we're keeping track of. All we need to do is return whether or not that size is 0. And now we can reuse this everywhere. Instead of checking to see if the head is null everywhere, we can actually call this. If this is empty, and now it gives it a little bit more semantic meaning to us, that if the list is empty, of course you can't remove from the head, so we need to throw an illegal state exception. Or up here, we didn't have an exception up here, but down here, if the list is empty, then we can return a string representation of an empty list. Okay. All right. So, remove from head, insert at the end. That's called the tail. So what does that look like? Well, let's go ahead and look at that visualization. I'm going to go ahead and insert at the tail here. I'm going to insert 42. That was a little fast. Let me go ahead and insert again here. Insert after the tail. I thought it would visualize. Okay, it's cheating here and jumping immediately to the tail. But that's not how, and that is a possibility. And we could keep track of both the head and the tail so that we could jump immediately to the end of the list, but I chose not to do that here. So one thing that we're going to have to do to insert at the tail is we're going to have to start at the head, traverse all the way until we get to the end here, at which point we can insert that element. So let me go ahead and copy paste this, insert at the tail. Right? Now, what is that going to look like? Well, it's going to look a lot like the string, the loop we used here for the toString method. Okay, so let's come up here, insert at the tail. The current is, we initialize it at the head. While the current is not null, then we go ahead and go to the next. Okay? And then once we've got that element, we can do something here with it. Current, let's create a new node like we did before, holding that item. And what we need to do is we need to, once we've got the tail, current, we'll set its next, set next, to be not the new head, but the new tail. There. And of course, we need to increment the size. Now you might be immediately thinking, oh, this is you might see the error here right away, but let's go ahead and see what it looks like down here. First of all, I'm going to go ahead and get rid of this stuff which we know is going to throw an exception. And in fact, let's go ahead. I'll put it up here. So we've inserted, a list that looks like this. And let me go ahead and get rid of this so that we don't have a bunch of print statements either afterwards. Again, let's go ahead and run this. And you see that there's our list. It's of size 10. Let's go ahead and try to insert something at the tail now. And we'll insert 42 here. And then we'll print it out. And in fact, let's print it out and also check out the size. Run this. And we're going to get another null pointer exception. So what happened here? I'm just checking to see how many people, 11 people are watching. Does anybody know? Unfortunately, we're on like a 10 or a 15 second delay, so I'm not going to sit here and wait for 10 seconds for anybody to answer. But you might be thinking, well, wait, we break out of this while loop here when current is null. So down here, current is going to be null. In fact, check this out. My IDE is noticing it. My IDE is noticing that there's a null pointer access here because after this while loop, the reason we broke out of this while loop is because current is equal to null, and so we cannot call a method on a null object, right? So we're going to have to take a different route here, and it's the same hint that I gave you as to the toString method up here. We don't want to go too far. We want to make sure that we go next until we're here, but we don't want to fall off the edge because I want this current here in order to create a new node and make that node point to it. Okay? So there are lots of ways that we could do this. We could say while the currents dot get next is not equal to null, then update it. All right? And let's see if this works now. Right? There. Right? So when we break out of that, we go to the next. We break out of this while loop now one less iteration, and so current is now pointing to the tail. Okay, so we create a new tail. We make the current, which is the current tail, set that equal to the new tail, right? And then we increment our size, and it totally worked over here, right? With no other modifications. But again, we need thorough testing here. What if I did that at the very beginning? Let me go ahead and get rid of that. I'll copy, paste this, and put it at the very top. Now, instead of 42, 142. And let's see if this still works. All right, null pointer exception again. Now, what's wrong here? Well, if we try to insert, if we try to insert at the tail in an empty list, well, current is going to be equal to the head, and if it's empty, then this is going to be null. So how can we possibly get the next node of a null reference here? We can't. So again, you're going to have to check to see if it's empty. If it's empty, then what I can do is I can create a new node, new tail, and then I can set this dot head is equal to new tail. Right? The head and the tail are the same thing. Or wait a second, that sounds eerily familiar here, right? Because this is then of course I would need to increase the size, and then I don't want to do the rest of this stuff here because I don't want to insert it twice. So I'll go ahead and hit return. Except that again, this looks really familiar, right? It looks like this. So if we've got an empty list, inserting at the head, inserting at the tail, those two things sound exactly the same. Let's go ahead and do some code reuse here. And now we don't have to worry about that. We're not copy pasting. We don't have a chunk of code that's the same everywhere. Right? There we go. I inserted 140. Oops, we got two 142s here. Oh, and then of course I need to return. Sorry, I still need to return because otherwise I'm inserting it twice. There we go. There, 142 is now at the end. So again, down here, what we're doing is we're inserting at the tail 142. If I print it out, then it looks like this, right? And then I print it out again. There's no need to do that a second time. And then I go into a loop to insert at the head 100, 90, 80, 70, all the way to the end. And then I insert at the tail here 42. That still works. All right, and the sizes here are all correct. Okay. All right. Well, that's insert at head, remove from head, insert at the tail, insert at the end, right? We have to keep. We might have to keep track of the previous, or we have to stop short. Is the route that I went? Let's go ahead and generalize that even further. Right? What if I want to insert at an arbitrary index? So I'm going to actually put that up here at the top. Public void insert at index. There's my item, and here's the index at which I want to insert it. Now, very similar to the array-based list, I'm going to want to make sure that I am checking my indices here. Right? I'm going to copy, paste that code because it's basically the same thing. If it's greater than the size, then or if it's negative, then I'll throw an illegal argument exception. You can't do that. Okay. Now, before I do this, inserting at a particular index means that I'm going to have to find a particular node, right? For example, let's go ahead and come back over here. And if I want to insert at index 0, then that's basically inserting at the head. If I want to insert at index size, then that's basically inserting at the tail. Let's look at this from a more general perspective. 0, 1, 2. Say my index is 2 here. I want to put this. I want to put it right here. Let's look at what that looks like first of all. So let's see. There's index 2, and we'll insert 72. Right? All right. So did you see how that worked? First of all, I had to find it. I had to find that node that was at that index. So that tells me, wait a second, maybe I should focus on that subproblem first. In fact, that subproblem is going to be useful later on because you want to get stuff out, right? So we'll go ahead and hold off on this for a second, and let's go ahead and solve another problem, a sub part of this problem that then we can reuse in a lot of different places. Get element at index, right? T item or index. All I need is the index, right? And it's not going to be a void function. We're going to return the actual item at that index. Okay. So forget about that for a second. Get an element at the index. Well, first of all, I need to find the element at that index. And we need to check our indices first. If the index is negative, then we throw an illegal argument exception. If it's greater than or equal to the size in this case, greater than or equal to the size in this case, then it's out of bounds because if there are 4 elements in there, the indices are 0, 1, 2, 3. If you ask for something that exists at 4, then we're going to throw an illegal argument exception there. So we know at this point that this must exist. So my first step is to find the node at index at the given index. ... Okay. Well, I could do my cut and paste while loop here, and then also keep a counter, or I could roll those two things in to the same thing and use, instead of a while loop, use a for loop, right? For I, running from 0, I is less than index I plus plus, okay? Now we may or may not be off by 1 here. We're going to have to test this out, of course. I'm just going to go from the current to the currents next. Now, if the index is 0, then let's think about this before we actually test it a little bit. Do some ad hoc testing in our heads here. What if the index that I'm asking for is 0? Well, then that means that this loop will never execute. And, well, what's that index 0? The head. So this works. What if it's at 1? Then this will increment once, and so we actually go from the head to the next, and we get the element that we're looking for. Okay. Now, so I'm convinced that it works. Let's go ahead and return the current node's item. Okay. And let's go ahead and test this. So now down here, I've got a list at the end. I've got a list of 12 elements, 10, 20, 30, 40, 50, et cetera, et cetera, et cetera. Let's go ahead and test some things out here. So int x is equal to list.get element at index. Let's go ahead and get that first element and print it out. Remember, we're only getting it. We're not actually, deleting it. So we're not modifying the list. We're just getting the first element, printing it out, and 10. That works, right? Of course, other corner cases that you might want to test are, well, what if we ask for something that's negative and we get that index out of bounds exception? What if we ask for something that's way beyond the size of the list? Again, we get that. Even if we ask for something at index 12, remember there are 12 elements in there, so index 0 to 11, 12, that's out of bounds. So let's ask for something in the middle to see if this is testing correctly. 5. 0, 1, 2, 3, 4, 5. We should get 60 back. Let's go ahead and test it and see if we do. And yeah, let's test another edge case here. Remember, 12 would have thrown an exception. Let's ask for the last thing, 42, at index 11. Right? And we get it successfully here. So I'm convinced that this implementation up here works, that get the element at the index. Now, how can we use that to our advantage at insert at index? Well, I want to get that element so that I can make this thing point to it, right? So what if I tried this? What if I tried this dot get element at index and at the given index, right? Well, what does that return though? That returns an element of type T. That returns an actual item, right? And this is the item up here, the old item, I'll call it, right? That's not really going to help me because what I need access to are these nodes. So let me go back and refactor this. This seems like a really useful piece of functionality to have in my list because you do want an index-based retrieval method. But to make it even more general and more useful, let's add another version of it. Get the not the element at index, but let's go ahead and get the node at an index. And instead of returning the item, we return the actual node. Otherwise, the entire thing is exactly the same. That should be sending huge red flags in your head. Why do we have the same code, the same chunk of code here, all of this stuff repeated here? Right? One of these things should be calling the other. Now, could I call get element at index from this method over here? Probably not, because all I have access to is that actual element, and I've lost the information about the node. So just in the other direction. What I can do is I can get the node. I can let's go ahead and get rid of all this. Node T relevant node, right? And I'll call that other function to give me that node. And then once I've got the node, I can open that node up and get the actual item. Return relevant node dot get item. Right? I just did that in 2 lines here to illustrate the 2 steps. Get the node, then open the node and pull out the item and return it. I'm going to go ahead and make this even more terse by simply just returning get the node at index and then get the item from that node, and you're done. Another thing that I did here is I removed that index bounds checking, which is okay because it's done in this other function here. This element will then call this this method, and if the index was out of bounds, then we're going to end up throwing this exception here. One other improvement before I move on back to our original task here is, should I really be making this public? Right? Now, certainly, if somebody that's using this list is going to want to get, if they put items in it, they're going to want to get the items out of it because they're going to want to put stuff in, take stuff out, right? That's what the whole purpose of a data structure is. If you put stuff into it, it's just a black hole without the ability to pull stuff out of it. It's just a black hole in which you can't ever retrieve anything. But does anybody ever need the actual internal node representation of our list? Probably not. This is what's called a leaky abstraction. That I'm basically, if I make this public and I allow you to get the node, or I force you to get the node, and if I didn't even have this available, I'd be forcing you to get the node and then opening up the node yourself and getting the item out of the node. So I'm not going to do that. I don't want to have a leaky abstraction. What I'm going to do is I'm going to make this private. Right? It is perfectly fine for my public method over here to use it because it's part of the class. But now I'm ensuring that nobody outside the class can break encapsulation by getting the node and then screwing up the internal representation of this list. Okay? All right. I am pretty convinced that now, of course, we might have some regressions here. So let's go ahead and run this again, and we should still get 42. Great. That still works. Now back to the original task at hand. I want to insert an element at a particular index, like we did over here. We inserted 42 at index 0, 1, 2. Okay? So here I'm going to have a little bit different bounds checking because if it's equal to the size, right, then that's okay. That's just inserting at the tail. In fact, that's telling me something here. Let's handle some corner cases maybe. If the index is 0, then you are asking me to insert it at the beginning of the list, inserting it at the head, right? So this dot insert at head item. Otherwise, if the index is equal to this dot size, then that means that you're wanting me to insert it at the tail, at the end of the list. This dot insert at tail. Otherwise, it's going to be somewhere in between. It's going to be somewhere, and of course, if it's an empty list here and you insert at index 0, that means that you're going to be inserting it at the head. All right, insert at the tail calls insert at the head when it's empty, but that doesn't matter. Otherwise, you're going to be inserting it at somewhere, right? So let me pull this code over here. There's the element at that index. Let's go back over here and think about this. So suppose that I wanted to insert, and we'll do this one more time. Let's remove. Or actually, let's just go ahead and insert another item here. 70, or let's go with 99. Right? At insert 99 at index 2. Right? So we're going to replace, or we're not going to replace 72 here. What we want to do is we want to shove 99 in the middle here. So we're going to have to find it, which we've already taken care of. And then we're going to have to make, let's go ahead and run this. Go. There we go. Once we've found it, then what we're going to have to do, we make a new node and make that new node point to the old one. So let me go ahead and take care of that. There's the old, and I don't want the item. I actually want the node. Right? So old node, right? And we'll not get the element at index, but we'll get the node at that particular index. Let's create the new node. So node t new node is equal to new node of that element item. Now I've got the old node. What I need to do is I need to make the new node its next. So set its next to be the old node. And that's only half the battle here, right? If I could have slowed this down, let's go ahead and, can I go back? Step backwards. There we go. I can step through this thing. I've basically done this now. I got this node right here, and then I created this new node, and I made that new node's next point to this node up here. The next step is to make that other node, the one behind it, point to the new node so that you can actually achieve the insertion here. Right? But how do I do that? The old node, I need its previous element. And there are doubly linked lists. We'll talk about that at the end. But in this case, I only have a singly linked list. It only goes forward. Right? So what I could do is I could say, okay, well, I also need that other node, old node. I could go previous node, I'll call it. And then I'll rename this one current node. Right? And it's at index -1. Right? And then I will set the new node's next to be the current node, and then the previous node, I'll set its next to be the new node. Right? And that's basically what this next step does. This is the previous, right? And I will make it point, there's the previous. It's currently pointing to the current node, and so I'm going to make it repoint to this new node, effectively making it look like this. Okay, And this will work. Let's go ahead and test it out, and then we'll try to optimize it. We'll go ahead and say list.insert at index 2. We'll put in 99 at index 2. So that should be then 0, 1, 2. It should be 10, 20, 99, and then the rest of this stuff. So let's go ahead and make sure that it works by printing it out, running it. So 10, 20, 90 is now, 99 is now at that new index there. Right? And of course, if I insert it at index 0, then it's inserted at the head. If I insert it at index 12, that's inserted at the tail. And then, of course, you can test every single possibility here. There's 99 at the second to last one, etc. I'll go ahead and keep it at 2, though, for this testing. Okay. Now, some optimization here. Suppose that there are 1 million elements in here, right? Now you're going to have to traverse, and that you want the index at like 500,000. So basically, you're going to do 2 traversals. You're going to do 500,000 traversals to get the previous. Start over at the head in this function, and do another 500,000 traversals in order to get the other one. Why do that when you've already got access to the previous? You can get access to the immediate next node by saying previous node dot get next. Right? Now you're only doing half as many traversals. You're still doing 500,000 traversals over here, but with this design, there's no way of getting around that. Right? And we want to make sure that this still works. There we go. It still works. All the edge cases would probably still work too. This is ad hoc testing. It's basically just sanity checking to make sure that everything works. This is not proper testing. You should set up repeatable unit tests to make sure that all of these possibilities are resulting in the behavior that you expect. So that if you do go and make changes and iterate on your design, change it, you add something new, then you have a test suite that you can test all those regressions. Did I break anything? Okay. But otherwise, I'm pretty convinced right now that it's working. Not entirely convinced because I don't have proper unit testing, but so be it. I automatically got my index-based search, the retrieval, right? By doing an index-based insertion. Now let's do an index-based removal. We've already got the remove from head. I don't remember if we did remove from tail, but we could certainly do that. In fact, before we do that, let me rethink this. Insert at head. Well, no, it's okay the way that we've got it here. Basically, we could change it so that insert at head actually calls insert at index with an index of 0. But then we wouldn't be able to call insert at head anymore, so I'd have to actually put the logic of doing that somewhere in here. And then we could collapse this logic down and make it much simpler. And in a real implementation, that's exactly what I would do. I would try to get this down to as many or as few edge cases or exceptional cases, like a bunch of, now I've got 3 cases here. I'd probably try to get down as much as possible. In fact, insert at tail can probably be taken out entirely. All you have to do is make sure that you don't go to the next because there is no next. All right. Actually, no, you don't even have to do that because if this is null, there is no next, then you're just simply setting equal to null. So I'll leave that as an exercise to improve on this design to you. Okay. But otherwise, let's go ahead and do an index-based removal. Right. So instead of inserting at head, remove from index. And we don't need the item anymore, just the index. And we will but we'll go ahead and take the same design as we had before of returning the thing that we're going to end up removing. First step is to find that element, which we've already done. Get the node at that particular index, which already does our bounds checking as well. So node t node to remove is equal to get node at index, get that the node at that particular index. I'm going to go ahead and save off. Actually, we're not going to destroy that node until the end. Java Virtual Machine is going to destroy that node. So let's go ahead and go with node to remove dot get item, and that's what we're going to end up returning. Oops. There we go. Okay. All right. There's my node to remove. I'm going to get, but now I actually need to remove it. Let's look at what that looks like visually. So let's go ahead and pick on 0, 1, 2, 3, 4 here. All right. So let's go ahead and remove the element at index 4. So of course the first step is to actually find it. And let's go ahead and pause when we get there. Oops, went too far. So once we've found that, we've got a previous, we've got this node that we want to delete, and we've got the next. Let's go ahead and look at it visually what we're actually going to want to achieve here. We're going to want to make the previous node point to the current node's next so that it effectively disappears. Now, if this were a programming language like C or C++ and you were doing this implementation, you'd of course have to clean up that node, free up that memory. But with Java, it's all taken care of for us because of automatic garbage collection. So let's back this up a little bit. Now, I want to remove this node, but I need access to this node. So same problem as before with the insertion. I want to keep track of this previous. So maybe I don't want the node to remove. I want the previous node. Right? And I will get it at the index -1. Right? This may or may not cause problems here in a second, but we can go ahead and get the current. And instead of getting getting that, we could go previous dot get next. There we go. Okay. Now the current, that's what we want to return. That's the item that we want to return. Now, what I want to do is I want to make previous point to current's next node. So previous set its next node to current's next node. Now, if we were deleting the tail, this would be perfectly fine because current is, if we're deleting the last thing, the tail that is, then current's next node is null, and so we set previous to equal to its next equal to null, and we're good to go. But what if we're trying to delete the head? All right. So let's go ahead and test this out and see if this works. First of all. So let's go ahead and pick on 0, 1, 2, 3, 4, 5. Let's go ahead and pick on 50. So let's go ahead and remove, not remove from head, but remove element at, or remove from index. And then the index there was 5. All right, so we would expect that 5 is gone. And if we print it out, and the size should be decremented here. So that's probably something that we need to take care of here. Whereas 50 was here before, and it's of size 12. Now 50 is gone, but the size is still 12. What did I forget to do? Again, on a 10-second delay here, so you're not going to be able to answer. But where was that removed from index? There we go. Once we're done, then this dot size, right, minus. Right. That might actually be something that we forgot about before. Let's no, we had remove from head. That's the only other remove method I believe that we had. Yeah, and we definitely decremented the size. So let's run this again. See that the size is now correct. 11. Good. 50 is gone. Right. But let's go ahead and test this out. What happens when we remove from the head? Okay. So it was 10, 20, 99, 33. I'm removing 10. Let's see here if it works. I should get 20, 99, 30, and a size 11. But I get another null pointer exception here. Index out of bounds. Let's follow the stack trace here. I went to remove from index. The index was 0. Well, that calls get node at index with index -1, so -1. So of course we're going to get this exception because index is now -1. All right, that's not what I wanted. So let's go ahead and go back to that line that threw this exception right here, right, that started this all off. So again, a corner case here. If index is 0, well, we already have a remove method to take care of that for us, right? Remove from head. And then, of course, we want to make sure that we stop, and so return. Except that we do have to return something here. So I will save that off. Let's see. Are we taking care of? Yeah. If it's empty, then we throw an illegal state exception. So let's go back to where we were. Before we remove from the head, we need to save that off. So t item is equal to this dot head dot get item. There we go. And then we can return that item. And now when we run this again, we've taken care of that one exceptional case, that corner case of removing from the head. What about removing from the tail? Let's test that. So if it's 12, then we would end up removing item from index 11. And we ended up removing, I guess there are 12 elements in there. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so 12. The size is 12. I screwed up somewhere, though, because the size is actually a 13. 3, 3, 3, 12, 13, yeah. So we need to go back and fix that. But there, now you see that 42 is removed based on index 11 here. I'm pretty sure I know where the error was. Let's go ahead and check from top to bottom here to make sure that we are doing our bookkeeping on size correctly here. Get element that has no effect on the size. Remove element from index. Of course, we're decrementing it. Insert at index. That's going to increment it. And if we're doing it special here, insert at head, insert at tail. Those take care of the size. Go back. Insert at tail takes care of the size, right? But the one place that we forgot about it was here on the other case. This dot size plus plus. There we go. And now we should see this 13, that become 13. This should become 12. And there we go. Now it's fixed. All right. So that is the basic functionality of a linked list. You can put stuff in, you can take stuff out, you can remove stuff, you can retrieve stuff. The basic 3 or 4 operations that you would have with any data structure. The one thing that we didn't do is we didn't replace. So for example, what we could have done is we could say public t replace element at index. And we'll take an item that we're going to replace it with, and we'll of course also take the index. And I'm going to leave this as a to-do for you at home. Implement this. Right. Here's a hint. You could very easily get the element, get the node at that particular index, pull the element that's stored in that node off so that you can actually return it, and then replace that node with the item here. Right. So think about code reuse. Think about how you might implement this directly with a loop of some sort. But ultimately, you're going to want to replace that with some other code that we've already written, right? Just so that it compiles, I'll make sure to get rid of that. All right. So we could have a bunch of other convenience functions. For example, I could remove everything. I could do batch operations. Say that I've given another linked list, and I want to insert that linked list. I could splice it in. If I wanted to get rid of the entire list in one swoop, I want to empty out the list, right? I could do a bunch of other things that might be helpful, but at the end of the day, remember, don't reinvent the wheel. I'll call this names. Now, you're used to array-based lists, right? And that's the go-to that we always show people when we're starting out with Java here. But there's also a list implementation called a linked list, right? And it's a linked list implementation in the standard Java collections library. You can see immediately what it has, everything that a list has. You can add elements. You can add an element at a particular index. You can retrieve elements. Everything that you can do with a list, you can do with a linked list. The only difference is that internally, it is representing things as nodes. We can probably even take a look at it and see what its node structure looks like. Yep, it's also got a node structure. that is parameterized. It keeps track of the first, and it also keeps track of the tail. Maybe they called this first and last. They probably should have called this head and tail to be consistent, etc. Don't worry about transient. That's something else. But otherwise, you can see that their linked list looks a lot like ours. Let's take a look at what it looks like to insert add element at index. There's add all, add. There's an element, link last. All right, so it's going to the end of the list. To do that, it's keeping track of the last, so it's cheating because it's keeping track of the head and the tail, so it's able to jump to the end of the list and just add it at the end. Link before, all right? Then there's a successor node. I called it previous node. They're calling it previous as well. In fact, what they've done here, it looks like, let's take a look at their node implementation. They're keeping track of an item and a next, but they're also keeping track of a previous. That gets us into variations. That's called a doubly linked list. A doubly linked list is linked both directions. So each node has an element, but it also has a reference to the previous node, and it has an reference to the next node, so that you can traverse back and forth as much as you want. And that's what their implementation has done here. The other variants include circularly linked lists, where you start at the head, next, tail. Instead of the tail pointing to null and ending the list, the tail can point back to the beginning of the list, and so your list becomes basically a circle, right? And there is no head, there is no tail anymore. There's just an infinite circle, a circle that you can infinitely traverse back and forth and around again if it's a doubly linked list. Another variation is called an unrolled linked list. So a lot of authors will tell you mostly hardware folks will tell you never use a linked list because contiguous memory is much at the hardware level. It's much better. It leads to fewer cache hits and stuff like that. And they're right to a point. But why not have the best of both worlds? That's what an unrolled linked list looks like. So it has an array. Right, and that array can hold multiple elements. Instead of just a node that holds one element, you could think of this as a node, and instead of a node holding one item, it could hold a list, an array of items. So items, right? It could look something like that. Something very similar to what we did with the linked list implementation, right? But at the end of your array, you've also got a pointer or a reference to another array and another array and another array. Each one of these can be filled at capacity or maybe half the capacity. You can keep track of the size of each one of these so that you can check, well, if you were looking for the fifth element, right, index 4, then you can check, oh, there are only 3 things in here, so I can immediately, without having to traverse over this stuff, I can immediately jump to the next list and find there's my element that I'm looking for. So it's kind of a hybrid of these two things that that might have some use cases and it can be very useful. And the way that you usually use these is you tune them. So you make this array only as big as necessary, that can be held in one page of memory or something like that, so that you can minimize the cache hits or minimize cache misses and maximize cache hits, so that you're not hitting that lower level memory as hard. You're keeping as much stuff in memory as you need. A linked list does tend to lead to a lot of cache misses. And in real life, at the hardware level, that's where your performance is probably going to degrade the fastest. Finally, another variation on this is called a skip list. Sorry, there we go. So here's a skip list. It's it's not exactly a hybrid, but it is a linked list where these that you've got the main linked list here, but instead of having to, if you want the element at the end or at the middle, instead of having to traverse, 1, 2, 3, 4, 5, 6 to get the element in the middle, you've got a shortcut. Basically, you can skip all those elements, and then jump down to the middle here. Now, if you go crazy and make sure that you can skip anything, so that you can jump to any location with just one node traversal, you're back at square one. You're back at an array-based list. So there's got to be a healthy or a nice little medium between those two things. Some kind of Goldilocks zone where you're not jumping arbitrarily to everything. You're jumping maybe to the middle, but then of course then you have to do a lot more bookkeeping, because once you start inserting stuff over here, this is no longer the middle. So at some point you're going to end up degrading into an array-based list where you've got a skip traversal on absolutely everything. And you may need to then rebuild the data structure. But those are some variations that are actually used in practice. As we've seen, Java's linked list is going to be a doubly linked list. Circularly linked lists have applications in like round robin kind of situations where you just have to keep going around and around and around, kind of like a pull loop or something like that, or an interrupt request, or you just keep going around and around and around. Unrolled lists have applications in if you want to fine-tune stuff for that particular hardware where a memory page is a certain size. You can fine-tune it so that your unrolled linked list is exactly that size. So each one of those things will fit into a page of memory just nicely, and no wasted memory, not going across two different pages. And a skip list, if you want kind of the advantages of each and trying to minimize the disadvantages of each. Again, those are going to be that an advantage of an array-based list is that an index-based find is basically free. In fact, let's go ahead and take a look at our implementations again here. We'll revisit this when we talk about algorithms and algorithm analysis. But let's jump back up here to my actual stuff. Oops. And there's my array list. Remember that getting an element at an index is basically free because of random access. Over here, it requires get an element at index. Where was it? There it is. Get element at an index basically involves a loop. If you want the millionth element, you're going to be traversing 1 million times, right? So it's 1 million times as costly as an array-based list to find that stuff, but other stuff becomes super cheap. For example, inserting at the head. Insert at head, right? There's no loop in here at all. It's just just a few operations. It's just a bunch of reference changes. But over here in an array list, inserting an element at the start means that you actually have to shift things down. So if you've got 1 million elements in there and you want to insert it at the beginning, you're going to have to shift all of those 1 million elements down and then make room for it. So there are advantages of each, there are disadvantages of each, and that's why even Java provides multiple implementations. You've got an array list, you've got a linked list. You have to understand. You're not going to have to build these things going forward, but of course you should be able to. But in real life, you never reinvent the wheel. You just use what you have, and so you don't have to rebuild these things. But knowing in which situations you need to one data structure versus another data structure, that's where the real talent lies. Recognizing a situation where if I use a linked list here, it is going to be terrible performance, versus if I use an array-based list here, it'll be good performance. And then in a completely different situation, you can reverse those two and know well, in this particular use case, then a linked list is actually going to perform better than an array-based list. Being able to recognize those things is what our next topic is going to be all about, or our next major module is going to be about, algorithms and algorithm analysis. And in fact, I use these exact examples to motivate that talk. But otherwise, I don't see any comments from today. Thank you for watching. Of course, next week is our official spring break. So I will not be broadcasting. I'll be available on Piazza online. The LAs will not be holding virtual office hours on Zoom. I may jump on if I see a notification that somebody has joined the meetings. But otherwise, I will probably just be answering Piazza questions. So have as much fun as you can, but also try to stay in a routine, stay in a good routine with all of your other classes. Do have fun on your spring break, but be prepared to come back and make those proper adjustments now that we are all virtual. All right. Again, thanks for joining me today, and have a good one.